Okay, welcome everybody. I was waiting for Karen to start this thing off, and looks like she dropped out. Thanks, Leonard, for calling that to my attention. Um, we're just maybe a couple of minutes late getting started. We still have some people jumping on and joining us. We appreciate you attending this Ghost Rock Meet the SME. And we have the pleasure today of Leonard Schulenberg from VisiConsult um, talking to us about automation and automatic defect recognition. Um, I'd like you to please keep, hold your questions to the end. If you you can put some in the chat, we may be able to bring them up in the meantime. I'm assuming that's, of course, Leonard can change that if he wants to add questions throughout. But we're using a different meeting platform this time, so we'll be able to have questions directly instead of having to only go through chat. So anyway, we just like to say, also keep your cameras off because that saves a little bit on the bandwidth and makes things flow a little more smoothly. So, did I miss anything? I think we're ready to go. All right, Leonard, I'm going to hand it over to you. Feel free to introduce yourself, give a little more detail about who you are, what you do too will be good. Then we'll go from there. Thank you.
Perfect. Thank you, George. And I'll change what you said. You are fine. If you want to ask questions, feel free to do so. Either way, post them in the chat or raise your hand through the Zoom raise your hand function. I'll have an eye on it, and Karen and George will have too, I'm pretty sure. But feel free to ask questions in between or to challenge anything that I say, because we have a lot of time together. I'm bringing a topic that's potentially also controversial, and I would really like to tap into your knowledge and your opinions too. But that said, well, George asked me to say a couple of words about myself. I will keep that very brief because I want to talk about this exciting topic and not about myself. So my name is Leonard Schulenberg. As you can hear from my accent, I'm not from the US. I'm a German national, and I'm located close to Hamburg, in northern part of Germany. I'm with a company called VisiConsult. I will tell you a couple of words about that. But maybe about my background, I'm currently CEO of the company, and I have a background in informatics. So that's also why I know a little bit about this whole topic about AI, image processing, automation, and these things. But the purpose of this talk today is to give all of you an understanding of the state of the technology in automation, image processing, and AI. So what I want to try to give you is a broad overview what the technology can do, what it can't do, what the myths are, what the prerequisites for implementation are. And we will have a couple of deep dives. And some of these deep dives will be a little bit more technical. So I'll try to address this to all of you who want to get a good overview, but at the same time to all of you experts who want to know a little bit more in detail. Let's see if I will manage. So VisiConsult is a company that's headquartered in Germany, and we are consisting of 3 different brands. The brand that's mainly important for us in the NDT space is VC X-ray, where we build inspection solutions, automatic CT systems, 2D systems, inspection software, customized inspection solutions. But we also have a business unit, VC Count, in the electronics field, and VC Security in the public security EOD, so explosive ordnance disposal industry. In total, we are roughly 150 people located all over the world. We have a subsidiary in Atlanta where we have 9 amazing colleagues that are taking care about our US customer base. And that shall it be for today. What I do not want to bore you with is who we are, but I want to go into what this great technology can bring to. And I will talk, I'm a technology fan, and I will tell you a lot about technology and what it can do and why it's great today. But what we should always keep in mind that what we want to bring is value to our companies. So I will talk a lot about this concept of value generation. So what again is value? Value is benefit divided by cost. So value has to be measurable. Nothing of what I say today should be implemented because it's cool technology, because it's fun, because it's what everybody talks about. That doesn't make sense. It should be implemented because it drives value. So what is driving value? That could be higher efficiency, like a time reduction, an improvement on cycle time. It could be lower operating expenses, saving real money. And time is money, but time will only translate to money through other factors. When we are saving consumables, for example, we are immediately saving money. And then ultimately, that's why we all stand up in the morning, for we are in the quality industry. Ultimately, what we want to achieve is better quality. And what we want to achieve is less parts slipping through, making sure that this does not happen. We want to make sure that our companies deliver good stuff. So this is also adding value. And these are the three main value drivers. And we will come back to these value drivers throughout this talk, and we'll identify how digitalization, especially automated defect recognition, can help you to drive value for your companies. And this value proposition should always be the key factor for any change that we bring with technology. And always, I also want to show this first. These two things on the right are my most liked caricatures. So what I will provide today is a set of nails or hammers or tools. So everything what you will see today, from AI to cloud collaboration to robotics, is a tool we can use, but it's not always the right tool. So what we have to be sure, we do not see every, like if AI, for example, is the hammer, not every problem we see is a nail. So we should be really careful where we adapt it and where it makes sense. But at the same time, we should also be not like those guys that are too busy with the current way of doing and not implementing any improvements. So what we are looking for is the sweet spot in the center. The guys that are down here, they are on the left on this continuum. They do not want to invest. They are not investing. That's why they're accruing a lot of cost and effort. The person that sees in everything a nail is on the right side. So that person thinks to throw technology at everything. What we need to make sure, what is the right level of technology implementation for your company? And this is what I would like to challenge you throughout this talk. Think for yourself, or even write it down for every point. Does that make sense for me? Yes or no? And if the answer is no, that's not a bad thing. That is your answer for your situation. If the answer is yes, then you can explore what that means for you. But always keep in mind, all these things are only tools, and those tools are there to serve us, to make our life better, to drive value at our companies. That's very important. So before I go into the main topic of today, which is automated defect recognition, also called ADR, or artificial intelligence, AI, I will talk about some of the prerequisites, because that is really, really important when we want to implement something advanced as ADR. First of all, where do we come from in the X-ray industry? And again, our company is an X-ray company. I'm an X-ray guy. I'm not a UT guy. Everything I say today is strictly towards X-ray, and it might also be relevant for UT. It might not. It's out of my judgment. So what we are looking at is X-ray. Where do we come from? We come from very manual processes. Manual placement of film, manual placement of IQIs, manual placement of the IQ of the tubes, manual exposure, development, reading, archiving. The very, very linear scaling and manual process. So this is where the X-ray industry comes from, or inspection through X-ray comes from. What we have to do before we even can think about implementing AI or ADR, we have to move along this ladder. We have to move up. We have to start to first digitize the process. So digitize means moving from a physical form, the analog form, film, for example, to a digital form, which is using a digital detector to acquire the X-ray image. That's the digitization step, the absolutely first step. Without digitized data, you cannot, ADR, which is operating on digital data, cannot even work. So that's what you first have to do. But if you then have a lot of digital data, you need to archive it. You need to put it in a digital archiving system. You need to put it in a way that's machine readable, that you can find the data again, because otherwise you just have a big amount of data. So that's the digitization step. Digitize the imaging source, organize the information so that you can retrieve it later. The absolute prerequisite. And if somebody wants to start here. Then comes digitalization. So digitalization means we are starting to automate processes and then streamlining it. So this could mean if you first have brought a digital detector to digitize the acquisition process, then you might want to introduce repeatability. So repeatability means making sure if I shoot the same image of the same part, it always looks the same. I get the same view. So you could bring in robotics, you could bring in CNC equipment, right? So this will help you to optimize the acquisition process and to make sure you have a certain repeatability in your acquisition so you can apply automatic digital steps on there. Once you've achieved that, you've probably already achieved 70% of your value generation. Digitization probably gives you 20, 30% of the total possible value generation. Digitalization gives you another 50 to 60%. So you are already quite far without even thinking about AI, ADR, and these steps. And this is then when the digital transformation step comes in, really transforming the processes and the way things have been done so far. And moving from film to digital is not a transformation. That's just an iterative improvement of the same process. But moving to an AI-assisted evaluation process, moving to a cloud collaboration approach in evaluating data, that's transformation. But before you can go there, you have to look at the first two steps. And where we, as a solution provider, see most companies fall, if you are in step 1, but you want to go to step 5 immediately. That's typically when stuff goes wrong, because you can't just go from 1 to 5. You need to climb the ladder step after step. So this is why I'll go a little bit slightly into the digitalization step, and then we'll move into the main topic of today, which is artificial intelligence, ADR, and what to do with that digital data. And I've talked a little bit about the film example and the different process steps involved, and how digitization, bringing a digital detector, is shortening down the process chain and is reducing it, and then bringing in CNC equipment, automation, shorts it even further. And then at the end, the transformation part, or the industry 4.0, NDT 4.0 step, is bringing in something transformational like AI. And that's really changing the rules of the game, because as you can see, with every of those implementations, the amount of human involvement in that process gets less and less and less. So with good, we all have to think about where will be the human left in this equation once we go there. First, it's the film placement. Then it's the movement of the part and the movement of the imaging sets. Then it's the reading. Where's our part? And I can tell you, this is maybe the cliffhanger to the end. There will be plenty of room for us humans. AI is not nearly as smart as the mainstream media makes us think, even though we all see this chat GPT everywhere around. AI is very limited in what it can do, but it is relevant and it is there. So it's something we have to think about. What does this new tool mean for our job? What does this tool mean for our industry? And how can I personally grow and adapt to this new reality? Because whether we like it or not, this is a political debate, whether we like AI, whether we think it's good, it's right, that doesn't matter because it's there. It's a good discussion to have, and it's a discussion our politicians and the ASNT, for example, should have, the standardization committees, ASTM should have. But for us who have to live with that reality, we have to cope with that. So it's good to know about that and learn how we have to evolve to be in this world. So levels of automation, I've talked about that. It can be from very simple to higher, to robotics, to a little bit of touch, to no touch, a lot of different levels of automation. And this can go to a level that is 100% automated. So this is a video of an inline inspection system for the inspection of air ducts in an aerospace environment. And this is not a concept, as you can see. This is the reality already now. It's integrated into a flow line. It is connected to an MES system, a manufacturing enterprise system. And the system or the factory tells the system what part is coming. The system's choosing the right gripper, and the system is choosing the right program. And then the complete inspection process happens automatically. In this example, there is no human involved anymore. The system is doing a self-qualification and is making sure it has the right image quality, and then moving into the inspection process. Inspecting such a part with film in the past took this particular manufacturer roughly 6 to 7 hours. This time is down to less than 20 minutes. And this is what was done just with the acquisition process. It's very transformational in a way, but it's still just an iterative improvement. Just to give you an example, because today is not about automation, today is about automatic evaluation. But this is the enabler technology. As I said, 6 hours to 20 minutes, 14 hours to 4 hours. This is the kind of value generation that you can get. And remember, I said in the beginning, the main value generation does not come from ADR and AI. The main value generation already comes from automation and digitization as a first step. AI then is the icing on the cake. It gives you the last 20 to 30%, but the main part comes before. And this is exactly the enabler technology to enable fast and repeatable inspection processes, reduce part handling workload on operators, but also reduce part handling mistakes that might happen. And again, remember where on this continuum you are. Some of you might not think, yeah, but I produce 40 parts a week. Why do I need a robot? The answer is you don't need a robot. We have to look, where are we on the continuum? Are we a high volume producer? Well, then automation makes a lot of sense. Are we a low volume producer? Then it doesn't make a lot of sense. So that's important, always important to know. Where does that tool make sense and where it does not? So once we are done with automating the manual work, the acquisition process, we can look beyond that because we start to generate data. And if we think about an automated inspection equipment that generates huge amounts of data in real time, we might think, okay, but I don't have all these people reading those images at the system. That's absolutely impossible. That does not scale. I now need 3 evaluators where I before had 1, just because I tripled the throughput of the system. So what we have done, we've shifted the bottleneck from the acquisition process to the evaluation process. And that's when the next level comes in of digitalization, is that we are starting to connect systems, I mean, physical systems, but also digital systems through networks or even the cloud. So let's assume you're a global manufacturer. You have 2 sites. One is in, let's say, US, and another one is in China. So you have 2 systems working, inspecting parts. Let's say you have turbine blades. So you have your serialized parts. They move into your system, either through a robot or through manual loading. That does not matter. And they get inspected. So what you will have as an outcome is an image attached to a traceability tag. That's, for example, the serial number or the barcode of your part. So this data goes into a central storage location. And the central storage location is connected to review stations. And those review stations could be on site. They could be anywhere in the world. This also has the benefit, let's say you do not trust your colleagues in China. You don't have the people in China. You can do it from the US. It's not a problem. Somebody gets sick, you can do it from a different facility, because everybody can log into the same data pool and work on the same data and do the analysis. And once this analysis is done, the data goes into an archive, the inspection reports, the rework sheets, scrap documentation, whatever your process requires. And the process data goes back to the physical layer. So you have a dashboard on your shop floor and you say that part is released, that part is inspected, that part needs to go for rework, and you can show the rework data to your colleagues in the rework shop. You have full traceability at every point in the process. And gone is the time of lost paper sheets that are put next to parts. You just scan a barcode and you see the results. This is what digitalization offers you in the software or evaluation space. You are detaching the physical operation from the digital operation, which is the reading part. So all this stuff, both the robotics and automation, but also the digitalization in the evaluation process, significantly increase the efficiency and throughput of your system. And if we go back to the value drivers, efficiency, that was a major part. That's a major driver. There was another driver of value that was money or consumables, CapEx or OpEx. That could be film. A digital system does not require film anymore. A digital system does not require chemicals anymore. You will significantly save money on consumables, another value driver. Higher inspection quality. Well, if you have a very repeatable placement, it is very unlikely that a robot places the part wrong. That might happen. There are many reasons why this could happen, but it's very unlikely. So you will also eliminate some of these potential human errors that just happen to all of us. And then in the end, easier documentation, archiving of results, no more film archives, and all these things. So all these are great things. And then we might say, but wow, we are done now. It's great. We have a very digital optimized process. This must be Industry 4.0. And then I say, unfortunately, it's not. This is what we have been doing for the last 15 years. This is Industry 3.0 as best. So what comes next? And what is the problem we have right now? And I said before, we are shifting bottlenecks. With digitization, we shift bottleneck away from the pure image acquisition to the part handling. With the physical digitalization, we shift the bottleneck from the part handling to the evaluation. And this is where we are. We have loads of data, but we do not have enough people to read all that data. So what is the problem that we face? We are swimming in a data lake. We have so much data that we do not know what to do with it. And if we again look to mainstream media, what do we always hear? Big data is the new oil of Industry 4.0. I say, no, I don't say it. This is a dangerous statement because data itself doesn't give you anything. You need to order the data, structure the data. You need to know what you're looking at. And data can always overwhelm you. So we need to try to uncover the information from the noise, and we need to work around the lack of skilled personnel. We already have a lack of skilled personnel in our industry. This lack of skilled personnel in the next 20 years will get severely worse. We will have too little inspectors for too much work to do. And if we do not fix this problem, especially in the West, in the US, but also in Germany, we have a problem. There are countries that have a lot of workers. That's maybe India, that's China. That's really, really good for them. But in the West, we do not have these workers. So we need to work around this fact. And this is then where smart inspection comes in. This is where we employ tools like ADR and AI to help operators make decisions faster and better, but also to potentially make decisions automatically where it is permitted. And everything we look at now, keep in mind, this is a tool. You might work in an environment, let's say a defense environment or a special aerospace environment or space environment, where you're not allowed to have automatic decisions. Then this tool, automatic evaluation, is not for you. You might work in automotive, then you might be allowed to do so. That's great. But even in very highly regulated industries, you can always use assisted defect recognition. You can always use the assistance feature. And this is a bit like with cars. We start to see first self-driving cars. Starting to see, not fully working yet. But what we see in most of the cars sold now we see assistance systems, braking systems, lane keeping assistance. Many of the tools that make driving safer are in these new cars. And this is how we will see assisted defect recognition features moving into NDT as assistance features. And as we learn more about the performance of these features, we'll grow confidence. We build data around how good do these features work? And are they qualified to make certain decisions, yes or no? And I will get a bit into how this is done currently. But ultimately, everything we are talking about today, from now on, will be how can we use algorithms, whether that's classic image processing or AI, to make better decisions faster. So let's look at where we come from, because ADR is not a new term. Our company alone is doing ADR since 27 years. ADR has been done for a long time, especially in automotive casting environments like wheels, like die casting. It's a very frequent process. So I will dig into a bit what is the classic ADR we talk about, and what then is AI that comes on top. So classic ADR, it's how does classic ADR work? You take a golden sample, and the prerequisite is that you place each part exactly on that golden sample again and again and again. So then you draw regions of interest where you set certain filters, certain thresholds, and you say, well, in this area, I'm looking for this, in this area, I'm looking for that. And then you are doing subtraction and image filtering, and you are coming to a result where you are finding anomalies in the part. So what you are teaching the system is how should the part look like versus how does it look like. That works great, and it worked great. It just has some problems, because the second your part changes, because let's say your casting form changes a little bit, or you have some burrs on the part, or your holder has some wear and tear, you start to get pseudo defects because the part starts to look different. That's an issue. And it can be very slight differences that can cause big differences. Also, programming a new part takes time. And this can be up to 1 week for a part or 2 weeks. So it only makes sense for very high volume parts. So this is a significant disadvantage of classic ADR, classic image processing. And this is then how it looks like. Yes, you have a raw image, you draw an ROI, and outcomes is segmented and then measured defect. But ADR is not only defects, it can also measurements. So this is an example I brought you here from a company, Aptiv, doing plugs and electronics for the automotive industry. You could also measure things. So you can measure angles, you can measure distances and stuff like that. Also, this is ADR. So don't only think about porosities and inclusions and cracks, but this can also be measurement tasks like dimensional checks. Or another dimensional check in the defense industry. If you look at, for example, hand grenades, they are produced at a rapid pace. It's, I would say, impossible as a human being to possibly really by your eye identify all these hand grenades and make sure that some of these measurements are completely accurate. This can be perfectly automated with classic ADR, because the part is always in the same position, the part always looks same. It has to happen very fast. It's a great ADR application. Also, this, not a new thing. This system probably here that we built is probably 15 years old. It worked in the past. What you could do for verification purposes, you can build your own artificial defects. So you create your own defect, or you import the ASTM defect, you project them in the part, and you are verifying the performance of what you can do digitally. Because you are also a little bit in trouble because you need to verify the ADR. So what do you verify the ADR to? Against an operator, against known defects, and then what is a known defect? So this is one way to digitally verify your processes beyond other things, of course. And then there is plenty of other things you can do with ADR, like reading out numbers, reading out serial numbers, part information through text recognition, OCR recognition directly out of the part. All great things, but we are still talking about classic image processing. This is not AI, and I'll come to I'll come to that in a bit, because what then is AI? We hear this in the media all the time. AI is coming, AI is overtaking the world, general intelligence, will we all be jobless tomorrow? What is AI? So what I want to do today, I want to try to explain to you what AI does. And I want to try to explain that in very, very simple terms and with some real life examples. So those of you who are data scientists, bear with me. Some of that, what I'm saying, is not 1000% correct, but to give understanding for everybody, I try to break it down into simple terms. So if we compare, or if we talk about what should an AI do, and ultimately an AI should do a decision, and that resembles what a human would do. We humans come to decisions. That's the outcome. It's the same. You see the red thing is on both sides. An AI and a human both come to a decision. So how do they come to a decision? They come to a decision through a prediction. So what the AI and what a human is doing is giving a prediction of reality. And that's really, really important. Neither a human nor an AI is telling what is the reality. All of us humans and also the AI only give an interpretation of reality, a prediction. We think this is. And I think if all we humans, and this is maybe a political statement, would do that in our everyday life and say, hey, I know that I'm only giving a prediction about what's reality. I don't know the reality, but this is what it seems to me. Probably we would live in a more peaceful world, but that's not the topic of today. But it's really important to realize what you get from an AI is a prediction along with a probability. So how does an AI come to probability? With data. We need to feed, and this is where the big data part comes in. We need to feed an AI system with a lot of data. And how exactly that works, I will tell in a bit. But that raw data is hugely important. If we feed an AI the wrong data, we get the wrong output. It's very clearly. Same with a human. How does a human come to a prediction? Through experience. What is experience? It's data. It's things we have experienced in the past. I do this, then this happens. This is why we have trainings, on-the-job trainings, learning from experienced colleagues. He does that because of that. It's pure data that we work on. And if we are trained wrong, we make wrong predictions, we make wrong decisions. If an AI is trained wrong, it makes wrong predictions, it makes wrong decisions. So below there are a couple of real-world examples. In self-driving cars, the prediction would be, or the question is that an obstacle? Is that an obstacle? The prediction is yes, then steer. That's not an obstacle, keep driving. The prediction of reality. And this is what we see in the media when self-driving cars go wrong. They make the wrong predictions. The Tesla thinks that's not a human. It was a human. Wrong prediction, fatal outcome. Customer service, will the customer churn? Give a discount, like automatic customer service prediction, language translation. What are you saying? Trying to, from the sound waves of what you say, trying to make sense and transform this into a reply or written text. It all goes the same. So if we then look at speed and accuracy, and now this is a little bit misleading on the left because it seems the AI is superior to the human. That's not always the case. But if we're looking at a very narrow example where like big data is involved and a fast decision has to happen very, very cheaply, computer systems are typically superior. Typically. And again, that's in many cases not the case. Where humans are good is where we have a lot of context, where we have very vague data, where we have very sparse data, where we have the gut feel involved. That's where humans are very, very good because we have intelligence. And AI does not have that. And AI gets trained for one task. And once it's trained for the task, it's very, very fast. It's very accurate. It's very repeatable. And it's very cheap. So typically, where AIs really are doing great, if you look at the red bubble of machine learning, is where you have a lot of complexity, more complexity than our human brains can process because it's just too much in a too short time. We get exhausted, and that could be rules complexity, like like trying to adapt to execute 500 rules. We can't even keep 500 rules in our head. We can't even remember that. And then we have data complexity, where we have very, very complex multidimensional data that we as humans can't really process, because that's not what our brains are done for. We are not processors. We are not calculation machines. And this is where AI is really strong. If the complexity is lower, then rule-based machines are great, and rule-based machines is classic ADR. This is what I've showed you before, like doing real image processing tasks. And the human judgment, we do very good with ambiguous data, with data that's not clear, with contradicting data. That's where machines are not doing very well. And this is also why nobody really has to be afraid of AI, because somebody has to train the AI, somebody has to maintain the AI, and somebody has to tell it what to do. Because inherently an AI is stupid. AI is like a kid. We have to train the AI what it should do, and what the data is, and then make sure it does not go off track. So when we look at how does an AI make decisions, we start with raw data. We start with input, and then it goes through a neural network. And this depends a little bit on what architecture of AI you're working in. There's a lot of different things like convoluted networks and many others. But for the simplicity, let's go through a like normal neural network. So based on the data, we are going through a certain path through that network. And this is incredibly important if we look at these individual neurons, because neurons always take 2 inputs and have 1 output. And if you then look at the mathematical formula, an AI system, the math is very, very simple. You just take an input, multiply it by a weight, and apply an offset, a bias. That's all it takes. And this you do thousands, millions of time, and you're just readapting the weights. But this also shows if either the data or the weighting or the bias is wrong, you come to the wrong output. And what that means, I will show in a bit, and how we'll avoid that, I'll also show in a bit. But actually what happens through a training phase of an AI is to gain the right values, the right weights, and the right biases. And an AI is only as good as its frame. That means it's only as good as the data that we show the AI, as the boundaries that we give the AI. You can totally mistrain an AI system. It's just a tool that can be applied. And this shows it a little bit. If you have the same input, like 3 and 2 here, and you have different weights and different offsets, you come to completely different results. And I will share some practical insights, how we've seen that in our work with applying AI to X-ray images, how we have encountered human biases, how we have encountered inconsistency in decision-making, and what that does to a decision system. So if we wrap up the data portion, what do we need? What's the prerequisite? If you came to me today and say, I want to have an AI, what would I tell you? What would you need? We need training data. We need to have input data, and we need to have output data. We need to know, for example, this is a porosity, and it is, well, let's say different. This is an indication, and it's a porosity. So we need to know data. We need to have data that's used to train the AI. So it's put into the AI to develop the model. And we need to have data that's used to verify the model. And this is how it can be visualized. Put in the features of the training. So the features, the blue stuff, this is a structure, like something that looks like a porosity, and tell the AI, the red thing, it is a porosity. And this hundreds and thousands of time until an AI really knows, okay, that's a porosity. If I see that, porosity. And then the test data, you have feature set, you put in the model, and then you verify, if I give you an image of a porosity, do you really tell me it's a porosity, or do you tell me it's inclusion? So that's where we can test the model on its performance. And this we do a lot of times. We start to train the model. We adjust the weights and the biases. We do predictions. We measure and we measure the accuracy of the result. We provide feedback and we adjust. And this is why you need high performance computers during training, because this calculation takes part on graphic processing units, GPUs, graphics cards, and it's taking a long time. Sometimes these calculations can take a week to calculate the right weights, because we're doing this again and again and again until we have found the optimum in the system. So let's talk as we are going into, and again, I want to encourage you, whenever somebody of you has a question, post it in the chat, lift your hand, and I'm happy to take any question as we go. If not, there will be a session or a section in the end where we have time to discuss all these things. So as we are going into the X-ray world now, and back to the NET world, let's talk about terminology a little bit. So let's start in the physical world. We have, let's say in our world, we have a discontinuity. Could be a porosity, for example. We take the digital X-ray image, we are digitizing it in the digital space, and we are looking at an indication. There is something. There's something, and then we need to make an interpretation. First of all, is that relevant or not? Is it relevant or not? If it is relevant, it's a flaw inside the world, and then we need to make a choice. Is it acceptable? Is it rejectable? Rejectable, we have a defect. And that's incredibly important when it comes to accrediting AI systems, because we get this asked a lot. How can you accredit an AI system to make a decision on my part? And the plain simple answer is you cannot. You can't. What the AI system is doing, it's living in this red box. An AI system is looking at your image, finding all indications, and putting it in a list and on your screen. So the AI system tells you, this is everything that I've seen as an anomaly, as an indication in your part. The AI system does not make the decision. The decision can then be done by either a human, if you have an assisted environment, or through a rule set that is set by a human. Never is the AI doing a decision, because you can't qualify that. There is no regulations, there is no norms, no standards around that. How would an AI system make a call? You can't. The AI system can only provide the data that lets something or somebody make a call. And if that's a rule-based system, somebody has to sign off for that rule-based system. Some level 3 has to say, okay, these are the thresholds, these are the rules I put in, and then I statistically ensure that the input into that rule set, which the AI is giving, is correct with a certain probability of detection. So that's really important. As we are going forward, in the context of AI in X-ray, we are only talking about indication, finding indications. We are not talking about finding defects, because defects are down here, or we're not talking about decisions. So this case I'm talking about, I want to show you today, is a real life case, and we've got approval by our partner Pratt, PFW in Germany. Not Pratt, sorry. That was a jump in my mind. PFW, who are now part of the Hutchinson Corporation, and they produce air ducts and hydraulic lines and these things for an aircraft environment. And they've invested a lot into automation, into optimization, digitalization. So now the next jump would be looking at how could AI help us to make better decisions. So what we are looking at here is very challenging, super thin titanium welding lines. It's electron beam welds. We are talking about incredibly small defects, 1 to 3, 5, 6 pixels, sometimes less. So something's very hard to find on a high resolution detector for a human. And we'll talk about the same. We'll talk about the raw image. We'll talk about predictions. We'll talk about operator segmentations in this context. And remember what I said about how to train a neural network. We have an input data set, that's a training set that's used. So that data set is segmented by operators, by inspectors, and is then put into that data is put into the model, and then it's verified with test sets. And from these test sets, we are building statistics. And I will show you some of the statistics in a bit. What are the outcomes? Where do we stand in terms of performance? But first of all, I want to give you a little glimpse into how this would look in the real world. And this is just an implementation example, and focus more on what you see here in the center. What the AI does in this case, you click on a button and then it labels, it sets a circle around every indication it finds. And again, very important, I'm saying indications. I'm not talking about defects here. Just saying these are all things I think shouldn't be there. This is the first function. The second function is that you could segment all indications. So you have an overlay, let's say a green overlay on the defect, so that you can better see the defect on the black and white image. And there's a third function in this case, because the defects are so small that this was specifically asked. Set a green dot under the welding line, just to make sure I can easier see where the indications are. And what then happens automatically, all indications are measured, and they are measured in diameter. It's ferrite diameter, so something that's really applicable to porosities, and it's measured in areas, and it's measured down to the subvoxel accuracy. And as you then, through your arrow keys, jump from porosity to porosity, or from inclusion to inclusion, or whatever, or crack to crack, you can then make a decision: remeasure the defect, accept. Oh, sorry, no, it happens to me all the time. Remeasure the indication. Say yes, that is a real indication, and it should say, or tell the system, no, this is a false finding. This is not an indication, please remove it. And as you do that, you're going through and you're making all these calls. And as you then close the image and say, okay, I'm done, that information goes directly back into the training set. So what happens as you are using the AI, you might start with a prediction accuracy of 70, 80%. And as you use the system, you're feeding it more and more and more data, so it gets better and better and better. And I will show you where this can end up in terms of percentages. But that's roughly how it works. Yeah, and here's a little zoomed example where you have the measurement function, where you have the circling, and where you have the table with the summaries. But also, before I come to the values, there's obviously cases when it does not find something it should find. So let's assume these inclusions here. And you see here now we are not talking about, this is a positive image, so all these black dots are inclusions. They are not porosities, because they would be white. But here are some potential inclusions that were not be found. What is this? So let's go back to terminology. If you make a decision or a prediction, you can be right or wrong, and you can be right or wrong in 2 dimensions. First case is you have a defect / indication in your part. If you make the decision, this is really an indication, you correctly identified the defect. If you have no defect or no indication in your part, and you said there is no defect, you made a correct, or the AI made a correct decision. If you have no defect and you said, but there is a defect, you have what we call a type 1 error or a false alarm, a pseudo reject. You're creating a potential reject of a good part. This is not nice. This could cost your company money. This could create extra work, but it's not critical. A critical error is if there is a defect and the system says there's none. That's a type 2 error or a miss, a false negative. That is very, very critical. Those are the things we try to avoid in our NDT environment. And now you have to look at strategies. You have to look at, okay, what's more important to me? If you're an assisted defect recognition environment, you might not care so much about a couple of misses because you still have an operator, you still have an evaluator looking at it. If you're in a fully automatic setup, you would not want a miss to happen. So you would be much, much stricter with your levels of acceptance. And then this leads to the different clusters: true positive, true negative, false positive, false negative. And again, true positive, true negative, that's great. False positive, false negative, that's an issue. And false negative is the most critical issue we would look at. So this then gives certain metrics how we can evaluate the performance of an AI system. We have a true positive rate. That's how much, that's the percentage of the true positives that I found. False positives rate, the percentage of the false positives that I found. False negatives rate, the percentage of the false negatives that I found. And this is how we will, in the next slides, evaluate the performance of an AI system by looking at the rates at which it detects certain indications or certain defects or not. And for those of you who are very much into qualification, of course, there is probability of detection curves that are significantly more advanced than these true positives, true negatives scenarios, because we are on the indication base. So a miss on a 1 pixel indication is significantly less severe than a miss on a 20 pixel indication. So what the POD calculation takes into place is this curve. Like, you'll probably have a lot of misses in the very small area, and then you shouldn't have a lot of misses in the high size area. Keep that in mind as we are going through the data. And then ultimately, it's a trade-off choice that everybody has to make. What we as a solution provider, what our job is, making sure these two hills you see here, those two curves, are as far apart of each other as possible. So the overlap, the false negatives and the false positives, are as small as possible. But even no matter how good of a job we do, there is, with a certain probability, always the chance of having a false positive or a false negative. And now you might say, oh, but how can I then use it? But then my counter question would be, would you, for a human operator, could you say with 100% confidence that human never, ever makes a mistake, never has a false call? And this is why we have POD analysis. This is why we're looking at confidence intervals, because we've realized everybody, whether it's human or an AI system or an ADR system, makes mistakes. That's in the nature of things. So the only thing that we have to decide, what probability of detection is acceptable for us? Where do we set our threshold? And this is what has to be done. Assisted recognition, I might be a bit more tolerant to misses. I might not want too many pseudo defects because they are slowing me down. I set it this way. I'm in an automated setup. No misses are permissible, but I'm accepting a couple of pseudos that I have to reevaluate using human double scrutiny checks. And then we look at this data that I was talking about. So let me go through a couple of different indication categories. And the first one is cavities and porosities. And what you see on each of the slide is a little bit of quantitative data. The true positive rate in this case is 95%, false negative rate 5%, and you see the sample size. You see 1 or 2 examples of false positives here. And what you see here is a curve that's plotted over pixel diameter of the porosity and number of true positives, false positives, and false negatives. And I will not go into the exact details here, but what I want to point your attention to is that you have For example, you have in the 1 to 2 pixel range, you have most of the false negatives and false positives. Luckily, a 2 pixel indication is not even relevant for our customer. So, okay, what does that mean? We have a situation where the AI system is not performing perfectly in this range, but it's not relevant for us. And beyond that, you see a pretty nice curve. But again, you still see there is still a 5% false negative rate that needs to be addressed over time. It's work in progress. We come to particles of high density. True positive rate 92%, false negative rate 7%. You can see significantly more false positives here. And this is something that definitely has to be improved. But again, it's in a range of, let's say, 0, 1, 2 pixels that is not really relevant. So always what we have to decide, what is good enough for us? Is this good enough? Is this good enough for you? I don't know. But if you only care for defects that are 6 pixels and beyond, it certainly would be good enough. If you care for 1 pixel already, this would not be good enough. So then the AI needs more training and more improvement. Lack of fusion. True positive rate 99%. False negative rate below 1%. And then you can see all the false negatives and false positives are in the 1 pixel bracket. So what is this? This is dead detector lines. This is what's causing the misinterpretation. So the AI thinks a dead line on a detector is a lack of fusion because it looks very, very similar. And this is a great result. It looks how close you are, because no lack of fusion only has 1 pixel. So great result for actually quite complex defect to be found. Burn through, true positive rate of 1. 100% of all burn throughs were found by the AI. That's remarkable. You still have a couple of false positives, but they are also again in the 1 pixel bracket. This is again dead detector lines. So pretty good results, I would say, for something that's in a prototyping stage. And then I want to show you some pitfalls that could lead to wrong classifications. Dead pixels are classic. Is this a dead pixel, or is this a porosity? We humans know this is a dead pixel because there can't be a porosity off the welding line. The AI does not have this context knowledge. The AI is very good at spotting things that look like dead pixels. Look like porosities. So this dead pixel looks like a porosity. It gets found wrongly. So where does an AI have challenges? If you have 3 defects overlapping each other, that's complex. That's a complex rule that has to be taught into the AI. How do you actually evaluate that? And we posed that questions to our customers, and we got very surprising answers, because we got 3 answers from 3 people that were all contradicting itself. So it seems even in the broader concept, we haven't made up completely our mind what has to be done. And then there is things like low contrast. So this thing here, is this a porosity in between 2 other porosities? Yes or no? Some people would say yes, others would say no. And what we found out, that there's a lot of ambiguity and variation in the training sets coming from different operators. But this is another case when an AI might get confused. Again, another low contrast example, especially as we get to very, very small features. And then, as I said, dead lines in the detector. This is a dead line. Looks very much like a lack of fusion in certain welds. So something we need to teach an AI, as we would teach a human. Hey, if you see this white thing somewhere off the welding line, this is not lack of fusion. This is a dead detector line. You need to calibrate the detector. This an AI would have to learn, as a human would have to learn. And what was our biggest learning, is that we looked at the training data, and what we have done to get, remember, we need to get the human bias out of the data set. So how did we do that? We asked 5 operators, 5 very trained NDT inspectors, to evaluate the same data set. And then we compared this to each other. And that was very surprising. Even though there were very strict rules how the inspection had to be done, the outcome was what you see below. The red colored pixels are where there was no disagreement at all. Everybody did it different. The orange one, there was, most people agreed. The green one was, everybody agreed. So the good news is everybody found every indication. But there was a big difference between what the individuals said was right and what was wrong. And this is not surprising, because if you look at all the images on top of that, this is all the same data, just different window leveling, different contrast. So depending on what contrast or what window leveling you put, you looked at very different images, and you would make a different call if you look at the top one or you look at the bottom one. Very different perception. So what we then saw, okay, we can't just take the input from several operators. What we have to do is we have to objectify it. So we took that data and we had a master operator merging that data into a master version of the interpretation, and then even on top, adding a layer of filtering where we applied algorithms to say, okay, if we measure a defect, we start to measure it at 20% of the flank of the histogram dip. So we've applied some sophisticated algorithms to try to get the subjectivity out. And what was incredibly surprising is that the mean of the operators was closer to, or the variety between the AI and the mean of the operators was smaller as the variety between the operators. That for us was very surprising, that there's so much subjectivity in a data set. So, but then we come to qualification. How would we get an AI really qualified in our environment? And there's a nice standard, it's the E3327, and it solves some of the issues we run in, or it gives a good framework. Let's put it this way. First of all, it says, what is a match? What is a correct interpretation? And what you see here is that there is if this star is the interpretation, or is the center of the ground truth, and what you see here is another indication that got found. We have to make sure that they overlap to a big amount. If they do not overlap enough, then we probably have a false call. If they overlap highly, we probably have a good call, because it does not matter that every pixel overlaps, but just that it's right, that it found the defect. And then you have to qualify your systems. So first of all, you need an initial system qualification. So you have a representative inspection process data, and then you need to do you need to enrich it with operator performance data. You do the operator performance assessment, put this in the qualification, because as we do not have real ground truth, we are taking the known process, which is operator segmentation, as a ground truth. So we are saying, in the absence of knowing reality, we take the predictions of operator as the ground truth to measure the performance of an AI system. And then we take training data, we do software training. Then we have qualification data, and we do performance assessment of the AI. And then we compare that against the data of operators. So this is how you get a system qualified once. And this is according to E3327. If we do an upgrade, or an AI upgrade, a software maintenance, we need to requalify the system, because it might have changed. Similar as humans have to take an eye test can I still see what I have to see, or take a recertification test, an AI system has to do the same. Is it still running as it should? So there we take the qualification data, training data, and we have a set for requalification data, and we do the software change in the system, and then do the maintenance performance assessment, which is much smaller than the system qualification, and have a qualification. Ultimately, this is the same process, just as software maintenance requires less work than system qualification. And it always works the same. You have ground truths, you measure the system against the ground truths. Do I still see what I have to see? And what you then get over time, because the good thing is you can't send an operator every day to an eye test. That would be harassment. But you can actually have an AI system perform or evaluate itself on reference data sets every day. So what you are getting, as you are improving the AI or changing it, what you get is a true positive rate control chart, a probability of detection control chart. And then you could say, okay, I require for my certification the AI to run between, let's say, 87 and 100% TPR. I would say that's crazy low, but you could say 90 to 100. It does not matter. It's your values, depending on your process, on your risk assessment. And then you can plot over time, how does my system do over time? How does it change? And if it falls below the threshold at any point in time, you need to have corrective actions the system cannot process anymore. This is classical system performance evaluation that you can do over time. So how do you get to an AI system? You need to collect data. You need to label the anomalies or the indications. Then you objectify the data. That's what I said. You have 5 people labeling. Then you objectify the data into a master data set. Then we use augmentation, pre-processing. We kind of bloat the data set by applying noise, by applying gradients, by applying digital filters. We have our data scientists creating the model. We train the model, we analyze, we tune it, we retrain it, and that goes on a long time. That's a lot of calculations. Then you look at the results and you roll out the model and you verify it. And only after verification, it's good to be used in the wild, so to say. And if you then implement it, there's many ways. You can implement it on your desktop computer. I have it running on my laptop. Easy implementation, slow, cheap. You can have an inference computer. This is a high performance GPU workstation. Costs more, not cheap. Costs, I don't know, 5 to 10,000 US dollar to have a proper station. It's connected via the local network to the server or to a desktop computer. It's very, very fast, but it's more expensive. It's a little bit more effort. Or you can have a cloud solution, highest performance, but also some latency as you're transferring data to the cloud. You might have some data protection issues, but very, very fast and also typically quite cheap in the beginning. So there's different ways to do that. And here's no right or wrong. The question is always what suits your situation best. And then, of course, you need to measure the performance, use the E3327, calculate the hit rate or the TPR, compare that against your targets, and verify that. So talking about speed, and these are just case studies we've made. The average operator required roughly 10 to 30 seconds to evaluate one X-ray image, do all the measurements and markings and annotations. The AI needed less than 2 seconds. So there we come back to value. Fast, very high throughput, and on those defects or indications where it was trained, quite high reliability, and therefore also a fast return of invest. So again, we were hitting on most of the value drivers we discussed in the beginning. And most important is nobody would ever go, well, some people try, but it might not be the smartest thing to go from zero assistance to full automated. That just is too risky. What we always recommend, start from where you are now and implement an assistance defect recognition. Start to see how good is it working? And most of the time it's working pretty well. And in those times, it's cutting the cycle time per image, in this case, down from 60 seconds to 7 seconds per view. That's already a huge reduction. That's 90% or 80% of the total time. So we have already a big value generation just by the first step, and we do not have any risk yet, because there's always an operator looking on the data, looking on the image, and making a decision. No qualification needs, zero risk. We just need to make sure that the operators do not clock out and just start to click. Second stage, if we have all the data and we know the AI performs as it should, we move to the second stage. We start to show operators only views that have indications. So we are sorting out all views that definitely have no indications with a very, very high probability. So we probably want to say 99.9%. All of those images we do not want to see. This will eliminate, in this case, roughly 50% of all images to be reviewed by operators. So it's cutting the remaining cycle time or workload down by 50%. And then comes third stage. Once you really are sure, you have all the data, you have a couple of years statistics, you know that this is working, and you get approval by your prime or your end customer, you can implement stage 3. And stage 3 is full ADR, no human supervision. There you need to be really sure that what you're doing is working. And Gene posted a message in the chat. Sorry, I did not see that before. Does ground truth mean the actual factual reality of an indication? And I might not be, due to my language differences being a German, 100% sure what you mean is actual factual means, but you always talk about an interpretation of reality or a prediction. So what you are, when we talk about ground truth, it's operator inspection or operator segmentation. So it's the operator's interpretation of that image. We never have the real reality. We just do not know. I mean, we could cut open the part, but then it's cut open and we can't retry again. So what I'm talking with ground truth is always the best possible alternative, and the best possible alternative is human segmentation. And that's what's called, in our case, ground truth. We would love to have the actual factual reality, but most of the time we don't have it. Peter, hey, good to have you here. For stage 1, what is about bias from operators who are looking at marked defects from AI and might miss them unconsciously? That's an amazing point. And this is where, and in Germany at least, we have a human factors work group looking at that. How does this impact human decision making? And we might all know this. If we are driving with Google Maps, we are on autopilot, and if they tell us go left, we drive left, and we might make mistakes. So this is a severe issue, because if the AI is really right most of the time, people might clock out and say, okay, this thing is right. I mean, why am I even looking at this? Let me just press next. Get done with this faster and go to the break. This might happen. This is human factors, and we have to make sure that this is not the case. So what we've looked at, for example, we had a strategy with one customer where we forced the user or the operator to look at the image for 10 seconds before we showed the AI results. So that the person had to look at this and then had to look, okay, verify that, does that make sense? But to be very honest, this is something where the industry has to come together, where AS&T has to look at human factors, where ASTM has to work with. This has to probably be implemented through standards, because there are currently no standards. And Peter, it's definitely a concern also for us. How do we make sure, either by protocol or by design of the process, that this does not happen? But I don't have the perfect answer on that. Good, and this is a part of digital transformation. So implementing this, what you've just seen, these stages, that's really transforming the process as it has been in the past. We are building on top of the layers of automation, digitalization, process optimizations, and then we are building this disruptive layer on top. So How do you get to the implementation? First of all, you need to select a suitable candidate. My big advice would be, do not look for the hardest. Sometimes we see that people are like, oh, this AI thing will never work. Now I'll find the hardest application I can find in my company, and then I will prove everybody that this does not work. I'll tell you, it will not work. This is a self-evident thing that will happen. So always our suggestion, start with an easy case. Do not start with the most critical component. That DoD job you're working on might not be the right thing. Maybe it's the automotive cast part that you have. Start with something easy, start with something not super critical, and then start to prove out feasibility and have some quick wins. Start, learn, qualify, obtain approval, work from there, and then execute it. And then build on what you've learned, and then get the confidence, build the confidence in the team, get everybody on board. If you do it the other way around, it will probably fail, and you will not unlock the value of this. So I will go a little bit out of AI now and talk a little bit on how we can use that data, also using AI in the broader context of Industry 4.0 and driving improvements in our companies. So I want to talk about as we have this big amount of data, because be honest, even though some techniques say you have to mark every indication, but what we've seen many times, there's a huge indication and 5 tiny ones. What we've seen, people mark the huge one, reject the part, and close the case. That gets the job done. But what an AI would do, it would not stop after the biggest one. It would just mark all of them, no matter how small they are. So you would gain significantly more data on your part, and that data can really be used to improve the process. So if you have your physical part in your physical system, you're using digitization. This is the first step. You're moving the part into the digital space from the physical space. Then you have digitalization. You're applying digital processes, evaluations. You do stuff. You perform AI, and then you are driving change in the physical world. So this could be a casting machine producing a cast part, going into an X-ray. The X-ray has an AI running. The AI makes a decision, generates a lot of data on porosities, patterns, trends, and this data currently is thrown away. We're not using that. But how cool would it be if we could, in real time, inform the casting machine about the trends of its process capability? Hey, casting machine, your porosity rate goes up significantly. Hey, casting machine, we see cracks in your part. What do you do about that? And then it's the job of other people than NDT. Then we are out. Then it's the job of process engineers to make sense of that data, to use humidity data, raw material data, temperature data, to figure out why did it happen? How can we fix it? And guess what? How this is done? Also using AI systems. You need something to sift through all these big amounts of data. And when we talk about data, the faster we have information and data, the better. And this is where a lot of the problem starts in the current processes and where NDE or NDT is involved. We see stuff way too late. We can tell, oh, guys, 3 days ago, you produced scrap. And guess what? Probably for the next 3 days to now, you produce scrap, because we've only seen it 3 days later. So what we have to do, what we need is timeliness of information. We need to be, NDT needs to be as close to the manufacturing step as possible, potentially even in some of the preparational phases. Imagine you manufacture turbine blades and you have wax cores. How cool would it be if you could X-ray the wax core and throw away a wax part before you create a turbine blade? And not say after the fact, oh yeah, probably the wax core was broken. I have a core shift in my turbine blade. That might be a bit too late. So what we really want to do, we thrive to go towards preventative. That would be the wax core example, or even real time, or real time if we can't do a preventative data generation. And the later the data comes, the less value it has and the less we can do with that. So that's very, very important. And then coming back to the big data fallacy, data itself is not of value. What we need is information. So when we get a lot of data, we need to make sure we sort through that data. How do we do this? AI systems, algorithms. We need to arrange the data. We need to make sure we have it sorted. We need to present it visually so we can understand. And if you have a management presentation, then you might have to build a house. That's a joke, but definitely you have to transform data into information. And this, for me personally, is the biggest transformation for NDT as an industry, as a sector, is that we are not only an end-of-line quality assurance tool. And don't understand me wrong, this is still our core purpose. We have to make sure that no defective parts leave the company, period. But we could bring so much more value if we bring all that data to our organizations, and we could be of help. And we are not only seen as those guys that, you know, make good parts bad, but we are seen as those guys that help them produce good parts in the first place. And that's a huge change. And this, for example, is a couple of examples how this could look like. And these are real examples of say casting parts. So you could back project the defect locations in a CAD model. So casting engineers can look at, where my part do I see issues? Where are problems? And, you know, right now everybody has that. You know, the senior NDT manager saying, I think in that right area, you know, I see a lot of, I see a cluster of parts, I see a trend. And then the casting engineer saying, yeah, I think that's this part of the casting machine that needs to be fixed. What if we could provide data to exactly tell where a problem is located and then where it comes from? And then plot trends over time, see how the quality is developing, and really could substantiate that beyond just feelings and gut feelings ultimately. And this brings us to another area of artificial intelligence, automatic decision making, and that is using it on digital twins, either on the systems. That could be predictive maintenance, predicting when a detector will fail. How much pain would that save? If your X-ray machine would tell you, hey, I know that news is not good for you, but in 5 days, my detector breaks. You better get a new one. That still is no good news, but having a detector broken and production stopped is definitely worse news. So predictive maintenance is one thing of digital twins, but then also getting a digital twin of your part is very, very valuable. And I will skim through this a little bit just to give you an idea. So we've used digital twins in 2D and CT environments to optimize the results. So what we do there is we are using a digital twin of the system, like a CAD model, and we're using a digital twin of your part, and we are optimizing the inspection sequence. And we're optimizing the inspection itself and the image quality, also using artificial intelligence and algorithms. So we are simulating, based on the digital twin, we are simulating the part, the real X-ray image, and we are simulating the environment. And this would then look like this, where you have an AI system automatically generating trajectories. And what you see on the right is an AI system not properly told that you cannot go through an X-ray tube with a robot. Well, you can, probably once. But this is the constraints a system has to know. But this way, we can ask a system, hey, this is my part. This is my system. Please tell me the best trajectory to inspect this part. So what we have talked before with ADR is how can AI and ADR help you to evaluate images? Here we go one step further. How can AI help you to generate the perfect technique? Tell your system, I need 100% coverage. Please calculate the trajectories to have a technique to inspect that part. And we've proven that with CT, where we have tried to optimize trajectories to improve CT scans with sparse trajectories. So you can see that. Let me see. You can see that here a little bit. We are trying to to do an orbital CT, so not a typical Falcom CT, but different projections and different trajectories, and we're trying to optimize it in a way that we can do it with as little projections as possible. And this by itself will probably a 1 hour talk, but I just want to have the results be seen. What you see on the left is a baseline high precision CT scan, 1,400 projections. What you see on the right is a classic Feldkamp circular CT scan using 100 projections. And what you see in the center is an optimized trajectory CT scan using 100 projections. And yes, you see a little bit, you see some artifacts. It's not perfect, but you can see the features. So you have just achieved a 14 times improvements in cycle time, and you're still seeing your features through an AI-generated CT trajectory. And that is absolutely remarkable in my eyes, because now it's not only evaluating images, it's generating inspection programs. And then this leads us to image quality. How does the perfect X-ray image look like? So we have challenged our researchers with exactly that question. How does the perfect X-ray image look like? So they looked at histograms, they looked at exposure information, like an overexposure, min and max ratio of the gray value, number of peaks and stuff like that. And we have developed a tool that can calculate the right parameters, KV, MA, detector settings, stuff like that, for the perfect X-ray image. Because for every part, there is a force field like this, and there's an optimum. So this optimum can be found. And then it can be reached. So with this optimizer, we are optimizing the histogram and thereby the X-ray image. And you can see it's probably just, it's hard to see that on the right with the 8-bit environment, but you see the histogram on the top. You cannot distinguish the different peaks in this X-ray image. It's all very mushy, very muddy. And on the right, you can see perfectly distinguished edges or distinguished peaks. And then you might say, yeah, but I have X-ray experience. I can do this. And exactly, that's what experience level 2 and experience level 3 does. Finding the best views, finding the best X-ray parameters, and develop a technique. But we see already now that there is AI that can generate the perfect technique or the perfect trajectory, and we see AI that's based on that technique and that view is able to optimize the parameters to make the perfect X-ray image. It's far from perfect, but we see where the path goes. We see these tools coming. And if you ask me today, will these tools replace level 3? Absolutely never. Impossible, because of regulation, not and because of the focus of those tools. But will these tools be a great help to level 3s writing techniques being faster? Absolutely. Will they help companies to develop better inspection systems by having humans and a machine work together? Absolutely. So what we now have to think about, how does that change? How does that change our industry? How does that change our education programs? How does that change the skill sets that we need? And this is what we want to create awareness, and we want to talk about early. So there's another question in the chat. Ken, hey, cool that you're here. Since digital detectors do fail, can AI be developed to evaluate the effective conversation status of a TFT junction and the A to D device? Probably not in the exact root cause, but what the system can, what an AI can do. So what we've looked at, we can, for example, look at the dark current of a detector, and we realized that if there's a defect approaching in the detector, we see a change in the dark current or in the gain images. So you can monitor certain parameters in your detector to actually derive what is the health status. You'll not be perfectly able to say, hey, what's the status of my TFT connector? That not, but you are able to say with a percentage, how likely is it that my detector will fail? And again, we're talking about probabilities and likelihood. We do not know if it fails, but the likelihood increases that something happens, the probability. So digital twin value drivers. Create new inspection programs without occupying the system, collect information, digital twin of your part, but then also automatically optimize techniques prior to inspection and verify inspectability before really actually building the part. But then also the whole like digital automated tool set to be faster in creating and setting techniques. And I've planned to round it up with a very quick jump into computer tomography, and I've been doing this on an example of additive manufacturing, where CT is super important. And of course, everything that I've said before in the 2D space holds true in the 3D space. You can do automated measurements, you can do automated defect recognition, all these things you can do in the 3D space as well. I don't want to go much into detail, but it's exactly the same. It's just in a volumetric world and not in a two-dimensional world, but you can do measurements, plottings, okay, not okay decisions. All these things can be done. What is even going beyond that is that you can use the reconstructed models, the digital twin of your part, to actually really perform simulations, optimizations, and these kinds of things in the digital world, which even go beyond. So to set this into perspective, what we talked about today mostly was big data, AI, algorithms. But all this falls into the much bigger landscape of Industry 4.0, NDE 4.0. Robotics, simulation, cloud computing, Internet of Things, systems integrations, all these things come together. And really what we've talked today, AI, ADR, is only one aspect of improvement, of digital transformation. But also I want to remind again that to unlock these things, we have to get the groundwork right. We have to have a digital detector setup. We have to have some sort of automation system. And then comes the next level to bring in things like ADR. So to end our interpretation of how we make sense of NDE 4.0 and what we see as the most relevant drivers in X-ray. We've talked a lot about AI, that's clear, but CT, it was addressed, but also the cloud connectivity, the digital connection, robotics, simulation, automation, all these things are relevant in this world. And I see another question, Teho, do you think we can use simulation results to train AI for CT? Yes, excellent question. We actually do this already now. We are using a GAN network to simulate defects inside a CAD part, to simulate the X-ray image of the simulated defective part, and using that data to train an AI. So we are using an AI to generate AI-generated data to train an AI and to verify that. This we especially have to do if we have very sparse data sets that are not, we just don't have a lot of data. That's one way to do it. But also another application could be, we have never built that part, or you have never built that part. So how can we train an AI or see an AI feasibility if we just don't have any data? We need to be mindful, because this is never real data. It can be a source of, this can be a data source to improve the situation, but this is not real data, it's simulated data. So it yet has to be seen how effective it is. But yes, using AI to create simulated defects is absolutely possible. And again, I'm coming to an end. This is my last slide. And I really want to put this up again, because I get really excited on these things. Some might get really scared. I think both of it is not right. Nobody of us has to get scared. This is technology and it's coming, it's changing. I think we can see it very early. And now we all have to make sense of it. We need to see, okay, how does that affect me? How do I need to retrain? How need to I broaden my skills? What do I need to bring to our companies? But if it's applicable to your company, the worst thing that could be done is saying, oh, I don't want that. I'll not bring it in. because what will happen then, your competitor might, and that might be an issue because the value is generated somewhere else to the detriment of your company. And I want to remember, again, all these cool things we've seen, they don't make sense all the time. They make sense in many cases, but not all the time. They are tools. These tools work for us, and we need to pick the best ones for us that make sense for our environment and then apply them to generate value. And this brings me to the end. If you, as a digital person, if you feel free to add me on LinkedIn, send me a message. I would be happy to talk to you and learn what your challenges are. But I hope I was able to give you a comprehensive overview. And again, we were touching the surface today. On every individual topic, we could probably talk for hours. But my task today was to give you an overview about ADR and AI. So if there are any questions, just post them to the chat and I'm happy to answer. And I'll go through them. Ken, AI data security is critical in the cyber world of hacking into a company's data. Yes, that's a true statement. We are living in a world where cybercrime is a real thing, and we need to protect our data. And I hope all of you have good IT departments to ensure that. And not everybody needs to be in the cloud, and some of you are never will be allowed to be in the cloud. But then do it locally, protect your networks, and create and have backups. That's all I can say. Andrea, you presented supervised method for defect detection. Have you considered also unsupervised? Wow, this is a specific question. So just for all of you who do not know exactly what that means, supervised learning means that you have a human or a supervisor that classifies the data and tells the AI what is good and what is bad. Unsupervised data is you give the AI a lot of data and the AI figures out on its own what is bad in those images, what shouldn't be there. To be honest, we have fiddled around a bit with unsupervised learning. The results have not been so good. We think there is it's a combined approach in the end. We will start, this is our strategy, we'll start with a supervised approach to build a library or to build a generalized model for, let's say, casting parts. And then we will try to feed that generalized model a lot of data of casting parts and see if it improves themselves. But as we are in a regulated environment, and these things need to get qualified, we are very, very mindful of unsupervised things, because you might create a black box that you just cannot make sense of in the end. And for us, it's really important that we have this explainable AI approach to tell our customers, where do certain decisions come from? Why do certain things happen? And unsupervised learning might be a bit challenging. But again, great question. And I should, if you really want to discuss this deeper, I will put you in contact with our data scientists, and you could probably have a very deep and scientific discussion on that. But I would then not be the right person to really go to that level of granularity. Great, I see no more questions in the chat. If you can also feel free to unmute yourself and say something, because I'm pretty sure I have said some things that have concerned you, that you do not agree. And I think those are the most interesting. I would really love to learn where you think we got it wrong, or that statement is wrong, or we have a different view, because I think this is what everybody can really learn from if we have a controversial discussion and different views of the reality.
One of the things I was thinking just now about all this, you're talking about teaching the AI, so we can, I was likening that to how you would train or teach a child something. You start out, everything is 100% supervised. And as time goes on, child gets older, then they do some unsupervised learning, and people make mistakes, and we learn from those mistakes. Is that the problem is, how do you teach an AI to learn from their own mistake?
Yes.
That's Yeah, that could be that may be too much in depth, but
Yeah, it's,
that
George
would,
is exactly right. And currently the gold standard is the human. That's what it is. And this is also where all the standards refer to and the PODs refer to. That's what the ground truth is. So for now, I personally in NDT do not really see unsupervised learning as a too big thing. Maybe in the future, I think we are just scratching the surface on what AI can do. We are just a couple of years in this. Maybe in 10 years, it's completely different. But what I see after just a couple of years of investing R&D into this on our end at VisiConsult, the results are pretty remarkable. And it's some place also scary. It's just very, very high performance. And that is a cue that there's a lot of potential. I don't think we are even close to having all that potential being utilized. And there's a question, Musibur, can you use the ADR, the AI for different systems other than VisiConsult? Yes, we can. Our ADR could do that because the AI only works on images. The AI does not care about the system. The AI, the data input for an AI system is always an image. That's completely agnostic of where the image comes from, whether that's a VisiConsult system or not. So it's a different layer, and that's what I try to visualize with the system that I plotted in the beginning. You have a physical layer, that's where the system is, and as soon as the data is in the digital layer, you can do it whatever you want. You can have a human evaluate, you can have an AI evaluate. You are detaching decision from acquisition.
are there any more questions? Larry, that was awesome. I really enjoyed the your talk here. I learned a lot too. I think there may be another question. What
Yes,
format
again,
of it?
what
Mhm.
data format is needed? It could be TIFF, it could be Daikondi, it could be, we would prefer a 16-bit or like a 14-bit image like TIFF and Daikondi. But really, if these are very, very specific questions. If you want to learn more about that, send me an email or hit me on LinkedIn or somewhere, and I'm happy to send more information about the details of connectivity and how exactly that works. It's great questions, but ultimately, the AI does not really care what data format it is, whether that's a TIFF or Daikondi, because it extracts the raw data of that image, and from then on, the container it came with does not matter anymore.
Well, again, thank you, and thank you everybody for attending today and listening to the presentation Leonard put on. It is very well done. I like I said a minute ago, I did learn quite a bit. Things I really had not considered, a lot of what the AI world was up to, and it's a lot more advanced than I thought. So, so if there are no more questions, Karen, did you have anything? I think I saw you jump back in. I don't know if you're still here or not. It's not. Okay. Well, all right, everybody. Well, thanks for joining us. And one last thing, we've recorded this, and it'll take a few days, but we'll be putting it out on I believe Karen has a YouTube channel, and we'll make it available. If you do not have don't know how to get to that, you feel free to send me an email. That's george@hodgesndt.com. george@hodgesndt.com. Send me an email if you would like a link to the recording. And so again, well, if there's nothing else, I'll appreciate everybody's time, and we'll end the talk now.